Welcome back to the molpigs podcast. This is the first of our Labpigs series, and today our guest is Dominic Scalise, who will be telling us a little bit about his current research. Also with me today are Anastasia.
Hello.
Boya.
Hello.
Georgios.
Hello.
And I'm Will. Dominic is a postdoctoral scholar in Lulu Qian's lab at Caltech. He earned his PhD in chemical and biomolecular engineering from Johns Hopkins, where he was advised by Rebecca Schulman, and his BS in mechanical engineering from UC Berkeley. His work focuses on developing a stored program chemical computer and powering circuits using DNA buffer reactions. Dominic, hi.
Hi, Will. Thanks for having me.
Thanks for joining us. So perhaps you could start by walking us through the concept of a stored program chemical computer and telling us a bit about your work towards realizing it.
Yeah, absolutely. I'd love to. To get into what is a stored program computer, I think it's best to go back in time a little bit and talk about what were computers like before electronic computers had the stored program concept in place. So in the 1940s, the first generation of electronic computers were actually programmed by rewiring them. So a computer programmer would go into the room that is the computer and unplug all of the connections between the components and then replug them in according to their circuit diagram. So each computer program was effectively a brand new computer, a unique device just designed for that particular algorithm. And I think most chemical computers right now are effectively the same type of device. So we create a brand new chemical reaction network every time we want to do a new molecular algorithm. So this is frustrating because it takes a long time to program things, and they're error prone. And furthermore, the size of the algorithms that we can run is relatively small. So right now, if you want to make a brand new molecular circuit, it's going to take at least months if you're incredibly lucky, or quite likely years, or for some people, perhaps even a full degree to get from the planning stage to actually implementing and debugging and getting rid of all the leak in the circuit. And Boya, he's here as the one of the creators of the leakless DNA strand displacement circuit. So she knows how incredibly challenging and important it is to identify and address those leaks. That's where we spend a lot of our time. But the solution, or one solution to make programming a lot easier so that it doesn't take months and you don't have to debug the leak of your brand new circuit every single time, is to make one universal circuit that can run any algorithm and then feed that universal circuit instructions to tell it what particular algorithm to run. And it might take a little bit more time to get that one universal circuit running and debugged. But once you have it done, you shouldn't need to debug it every single time you want to run it. So there's a few quotes that I have pulled up here that from early electronic computers, computer programmers that I like, that capture this pre-stored program concept issues. Herman Goldstein, who was one of the computer scientists that built the famed ENIAC computer, said that the thing that makes the modern computer revolution possible is software. The older machines, before software, required one to clumsily perform hand pluggings of connections, which took hours, indeed days. It meant that programming was an art, a very dark art, and it meant that the total instructions that one could write was comparatively small. So he's expressing this frustration with the old style of programming. And then Turing has a nice quote I like, where he describes what it's like to program with a stored program computer. And he says, "It's intended that the setting up of the machine for new programs shall be virtually only a matter of paperwork. There will be no internal alterations to be made, even if we suddenly wish to switch from calculating energy levels of a neon atom to enumerating the groups of order 720. How can one expect a machine to do all of this variety of things? The answer is that we should consider the machine as carrying out orders given to it in a standard form which it is able to understand." So software is that list of instructions, the orders you're telling the computer to do, and a stored program computer is simply a computer that takes software and stores it in memory and executes those instructions. There's a long-winded answer to your simple question.
So what what's your approach to doing this? How are you tackling this problem?
Yeah. So the first thing you need in order to have a stored program computer is a lot of memory. You need a way to store your program. It's in the name of the computer, a place to put your software so that it can execute it later. And I spent a long time trying to figure out how do we get a lot of memory in a computer. For reference, most strand displacement circuits have no rewritable memory. It would be probably a Nature paper if somebody built a strand displacement circuit that could encode one single bit of memory in a bistable switch. That would be fantastic if someone does that. But we don't need one bit. We need hundreds or thousands of bits if we want to store a large program. Even what we would consider a relatively small program from an electronic perspective. So I think the first thing we need is a way to store a lot of chemical memory that can be accessed by chemical circuits. We've all heard of like terabyte in a teaspoon, George Church like taking all of the internet and compressing it and putting it onto DNA. But that doesn't work for a chemical computer because a chemical computer can't access that. You need an external synthesizer and sequencer in order to read and write that type of memory. So if we want chemical circuits to be able to do it, they need to be able to directly read this memory. So what I'm hoping to do is have the memory encoded on the surfaces of DNA origami nanotiles. That's one of the many things that attracted me to Lulu's lab is her expertise in these sorts of surface circuits, where each bit of memory is just represented by the identity of the strand at each location on your origami nanotile. And a single tile can have perhaps a 10 by 10 array. You have 100 bits of rewritable memory on each tile. And if you find a way to multiplex your tiles, then you can easily get from hundreds to thousands or quite a bit more memory. And that's the first piece. You need a way to encode all of your program. The second piece you need is the processor. So something that's going to actually go and execute all of those programs, all of those instructions. And for this, there's a few different approaches to it. You can have a circuit in solution, or you can do all of your computation on circuits. I started, all my work previously has been in solution, so that was the direction that I was thinking to go, but I actually think it's maybe more elegant to keep everything on the surface of the origami, make some things like parallel computing a lot easier. So in order to build that processor, now we need to make sure it's not too complicated. If you look at the processor inside of your laptop or a cell phone, they're going to be much, much more complicated than anything we can implement. And perhaps we don't even want to implement something that's exactly like a modern electronic computer. It's not optimized for chemical computing. So I'm taking inspiration from another very early electronic computer because in the 40s and 50s, electronic components were very finicky and very expensive. And so the first generation of computer scientists back then had to deal with the same sorts of issues that we were dealing with. Their bulbs would burn out instead of having molecules that had low yield. They would have poor connections instead of leak, but they still were dealing with fundamentally the same issues. So the design that I'm working off of is a Turing machine, but not the Turing machine. It's another type of machine that Turing designed called the Automated Computing Engine, or ACE. And this is when Turing took Turing machines, which are this abstract model, and decided, let's actually build this with physical hardware and optimize it for the types of hardware that we have. And he says that the Americans would make very complicated hardware so that they don't have to write elegant programs, whereas the Brits, they write really elegant programs so they can use very simple hardware. And because their hardware is so simple, they can build it cheaper and make it more robust, which is great when electronic components didn't work very well. So since our chemical components don't work very well right now, I'm thinking this is a fantastic model for what I'd like to do. And it actually lends itself very nicely to what molecules do. Essentially, every instruction in the ACE computer is a transfer of information from one location in memory to another location in memory. And we can think of this in a molecular circuit as just a reaction. Two molecules come together, they can transmit information from one molecule to the other. Or in this case, two nanotiles come together, they can transmit information from the surface of one tile to the surface of another tile. So it's very natural in a chemical reaction sense to build this type of transfer reaction. It's actually all you really need to build the ACE computer is a way to transfer information and perhaps transform it in the process of moving it over. So maybe you don't overwrite the memory that's encoded in one address or at one tile. Maybe you add the incoming memory into the existing incumbent memory. So my goal is to make, with these nanotiles, a lot of these transfer instructions and use it to build an ACE-style automated computing engine with molecules.
So I'm not completely aware of the ACE style, but is your idea to have a kind of centralized computing, central processing unit almost, and then memory around it that it interacts with, or is it more of an extended central processing unit and extended memory that interact with one another?
Yeah, so we could do a central processing unit. First of all, this will be all floating around in solution, so it won't be geometrically localized in one central location. But the other issue with a central processing unit is it can only do one thing at one time, and there's a bottleneck for it to access all of the different memory, so it's relatively slow. One thing that molecules do very well is parallel processing, as we saw with the Hamiltonian path problems in the 90s. And so it would be nice to have a processor design, but not make it just one central processor. Let thousands or 10 to the 14 processors operate on your memory all at the same time. The key thing, though, is to keep them all synchronized so that they execute your instructions at the right time, and one of them doesn't get ahead of all the others.
Synchronization sounds like a hard problem. What kind of approaches to that are you taking? Are you maybe taking inspiration from like the way the cell cycle synchronizes the entire cell, or what approach are you taking?
I'm not taking that inspiration, although that's a fantastic inspiration. Perhaps should be taken. But yes, you need a way to synchronize all of the components of your test tube instead of your cell. My first approach was more of a central unit, a single one, and I figured the problem of building a stored program chemical computer that can execute chemical software is already so far beyond what I know how to do. Let me just start by having an oscillator that synchronizes everything. So when the oscillator goes on, then everything fires and does its transfer instructions. But that again doesn't let you harness the full control of the beauty of molecular programming. So now my approach is don't have a central oscillator, but have each tile type have some communication. It bumps into its identical copies of itself. And when it bumps into enough copies that all have the same information on the surface, then it knows that it's ready to go for the next instruction. And this way you can synchronize and only have each instruction fire after everybody has caught up. So you have some asynchronous check before you run the next instruction. But this essentially is each type of tile turns into an oscillator on its own. The population will fire, wait for the next rest of the population to catch up, and then fire again.
Do you need if I'm imagining, so you will have on the surface there will be multiple computer component or multiple computers, so that can allow parallel computation. So your input to those computers need to be able to react to one specific computer instead of the others, or how do you control the crosstalk?
Yeah. So one thing that Lulu's lab has done, Greg and Philip in Lulu's lab have done, is DNA origami tile displacement, where you have tiles with particular addresses encoded on their sticky ends, just like Greg was doing on the Mona Lisa paper that you all probably have seen. And the tiles can find their appropriate address and just bind to those tiles. I'd also like it to be reversible, so they bind to their neighbor, transfer information, and then dissociate and go find another tile with the same address and keep communicating in that manner. So I don't want to have one big origami with 10,000 computers on it. I want to have 10,000 little origami, each with one computer on it, and have them all communicate by finding the appropriate address. Does that answer your question, Boya?
Probably yes. So so you're saying like imagine some input react with the computer that triggers tile displacement, so that computer is locked, won't be affected by other inputs, some kind of thing like that.
Well, the inputs in this case will either just be another tile that I've put in that has some information encoded on its surface, and then it can just go and bind to all of the input tiles of the many different computers and just transfer its information to those. Or you would have to have some other way to, let's say you want to sense some environmental stimulus, to get that stimulus encoded onto an origami first. I'm not focused on getting an external stimulus encoded on a surface. I'll just encode it myself, anneal it, and add it to the mixture. But I don't think that I want it to... I mean, I want the inputs to explore all of the different parallel computers, so I don't want it to stop after it's communicated its input to one. I want the input tiles to keep going and finding all of their potential neighbor tiles.
So let's say if you have an input 1 1 and input 1 0, and the first bit react with all the computer, and then the second bit, how do you differentiate the 0 and the 1?
Yeah. So each one of those will need a separate address, either along the side of the tile, saying the address 1 1 and the address 1 0. It can either be on the side of the tile, or it can be also doubly encoded on the surface of the tile. You can have the data 1 1 along with the address 1101, whatever it is. And that way you have a unique address and data code along each edge of each tile. So then the processors say, well, currently I'm looking for the instruction at 1101, and if it bumps into anything else, well, then it won't take that input at that time, because it knows what that particular processor tile is looking for. It only finds address 1101, and if it finds that, then it reads in its information and does whatever its computation is supposed to be.
So do you need to hard encode all the address hard code those address in your computer before you load the inputs?
So there's a few types. There's going to be the processor unit. That one, ideally, you should be able to make all of the processor mix and make one big batch of that and distribute it to everyone who wants to use it, and you never have to change it. After you've debugged it one time, you shouldn't need to make any of those connection changes. Then the memory units, those will have to have their addresses hard-coded beforehand, in the same way that your flash hard drive has, unique addresses for each one of its volatile bits. And those ones can either be encoded on the surface or on the edge of the origami.
Do you have a sense of complexity of your computer? And what's the limit?
Limit of?
How many bits of information you can compute, and how many components can be in your computer?
Yeah. So most of what I said is still theory. I'm hoping to get the theory out first. And then the experimental side is testing individual components. So experimentally, I can't tell you what the limits are. Theoretically, I think we should be able, using rates known about strand displacement and tile displacement and such, I think we should be able to get programs of the size of 10 to 100 lines. And those are much simpler than anything you can write in MATLAB or Python or C++, but I think would be quite useful, for instance, of making a gel robot that can take 10 to 100 steps or interact with the environment in 100 different ways, or a nanorobot that can sense 10 different medically relevant parameters in the body and then read them out later at a different time. Those sorts of program sizes I think are quite useful. I would be hesitant to say, I mean, on paper we could make it do whatever we want, but I'd be hesitant to say that would actually work experimentally for more than 10 to 100 lines. That's my current target.
So from a theoretical perspective, how does the stored program approach compare to like storing information in seeds for things like square tile algorithmic assembly?
That's a good question. It's a big question. It lets you keep updating the information. And it also lets you not keep the history of the information as well. So if you're doing computation in seeds, for instance, with the Woods et al. Paper, where they mix together a bunch of different tiles from a relatively small library and make it do like many different sorting algorithms and interesting binary operations. You need to keep the whole history of the computation, first of all. But for those types of approaches, you're still needing to build a larger computer in order to execute larger algorithms, generally. And I don't think you'll need to do that for this. You have more memory, but the processor size doesn't need to change. It's fixed regardless. I don't think that answered the question very well, but if you'd like to rephrase a little bit, I can take another stab at it.
Yeah. So at least from what you said, it sounds like in terms of the complexity of problems you could solve with a computer, your approach should scale a lot better.
Yeah, it scales. The nice thing about a stored program computer is you don't need to change the size of the processor, at least. You just give it more memory, which ideally is something very simple that's just encoding binary bits. So in the Turing quote, he says, let me flip back to it. There will be positively no internal alterations to make, even if we switch from calculating one thing to calculating something else. So it should be uniform sized. The computer should be of uniform size, regardless of what you want to execute. The cost, though, is then if you have a more complicated program, you need to give it more memory, which is like more tape in a traditional Turing machine. And you also need to give it more runtime. But the circuit itself that's doing the computation, that's doing the processing, doesn't need to change ever. And that means you don't have to debug it, re-find all the leaks, and make sure that it works every single time you want to run a new algorithm.
And so you've mentioned reversibility and history, this reminds me of some of, so for example, in DNA strand displacement, you tend to be making a lot of waste strands, and so species aren't necessarily that reusable. And in tile assembly or such thing with Woods, you have all that history data. So it sounds like you're coming up with a way to mitigate those problems. Could you walk us through a bit how exactly your computational components are working? Is there a lot of component reuse, or do you have to keep feeding in new components and restoring? And when you say reversibility, is there? Wait, that's another question. I'll let you focus on that for the time being.
Fantastic questions. I probably should be a little bit more humble. Many of the reversibility motifs are not mine and are not my ideas, so I should credit people appropriately. I think going even back to Charles Bennett, so this is like prehistory of molecular computing, it's been shown that if you have reversible computers of any type, they can be much more energy efficient. And so I think that's more or less the principle that you're alluding to. If we make things reversible, we use less energy, less waste. We don't have to provide it with as much stuff, and it can keep running for a lot longer. There are two things that we might want to have be reversible in this system. One is the tiles coming together and falling apart. That's relatively simple. That's just dimerization and undimerization. But the place where you could consume a lot of energy is with the reactions on the surface that are transferring bits of information from one tile surface to another tile surface. Many different labs are working on surface reactions on top of origami surfaces, and it's been shown in a few different ones of these papers that if you make the surface reactions reversible, then you don't need to irreversibly consume fuel strands from solution. But if you make them irreversible, then you can end up needing to consume quite a bit of energy from floating around in your solution in fuel strands or wherever you're deriving your energy. That principle predates me and is not something I've come up with. But there is an interesting complication here, whereas if you have all of your surface reaction, every one of your surface reactions be reversible, as they are in Lulu's 2014 surface CRN paper, then it's very energy efficient, but you're not driving your circuit forward very far. You're kind of waiting for it to do this random walk, and that can be very slow. Some people have found ways to make traps to try to get it so if the random walk gets to a certain place, then it keeps going forward. In this case, I think we need to have some sort of either entropic or energetic trap that is going to make the results of each tile transfer step collect on its edge. So the internal parts of the tile surface reactions can be reversible, but their results need to get stuck on the edge so that when they bind to their neighbor tile, they can quickly transfer everything to the next tile. They don't have to wait for things from different parts of the tile to catch up and transfer over. So in that sense, I think that it will require some irreversible reactions. Otherwise, things will be prohibitively slow and just never complete.
But you are targeting reversible computation then? You're kind of doing that fundamentally, or are you also considering irreversible computation, like irreversible computational primitives in this? Especially as you mentioned the Turing machine, which is intrinsically irreversible.
Yeah. I am planning to use other people's motifs that are reversible, but mixing in one irreversible step, which kind of breaks down calling the whole thing reversible. So I'm trying to keep the energy consumption as low as possible, but this one extra step means you will irreversibly consume some level of energy to drive everything forward. And so in that sense, it's probably a little less aesthetically appealing, but it's more practical in that it drives the system forward.
Well, in a sense, you do need some entropy method of driving that forward. If you had no irreversibility at all, then as you say, it'd be a random walk.
Right.
And the longer and longer the computation goes, because the time scales with the square of the number of operations, you'd never get to the end if you want to do a long thing. But have you looked into making the frequency of irreversibility of these irreversible operations dynamics? Maybe you could keep lowering it as you want to reduce the energy, or is that hard coded in either the program or the computer?
Yeah, that's a good question. I haven't explored dynamic reversibility, where it'd be pretty cool to let the computer decide when it wants to do irreversible steps. I haven't explored that, so I can't speak very well to it, but it certainly has tickled my imagination now that you brought it up.
It's like, what are the design principles behind when you're designing your stored program chemical computer? What are the design principles behind choosing an architecture, an instruction set? How do you actually decide, like, how much you want to leave for the programmer to do versus how much you want your computer to be able to do?
Yeah, there's a bunch of different ways to approach that. The instruction set in this case is stolen, practically plagiarized from Turing, except transferred from electronics to molecular computing. And the instruction set is a single instruction, and it's just transfer information from address A and put it in address B and find the next instruction at address C. So it's a single instruction, keeps things very simple. If we want to make machine level instructions that are more complicated than that, we could do so, but then we have to put in more complicated chemical hardware to actually implement those. And right now I'm saying that we're already at the limit of what is possible to build with existing technology. It's so hard to get it to work that I want the hardware as simple as possible. And I can't think of anything simpler, so I'll keep it at this single instruction set, just a transfer instruction. But you could get more advanced instructions if you build up the programming pyramid and no longer have a one-to-one correspondence with the machine level transfer instructions, but you can have addition and subtraction. You can have if statements. You can build up these transfer instructions towards those types of higher levels, and then you could keep building up multiplication or I don't know, much fancier types of instruction sets at that point. But that's really compiled down from a human readable programming language down to the machine level or the assembly level, where you have one transfer instruction actually equals one tile binding, one hardware step like that. You could, though, then say it invites the next question of why not have everything compiled down? Right? Like, why even have any machine level instruction? Why not just build everything with one very large Boolean circuit, maybe with some memory device to allow you to do sequential logic as well? And I think that's valid in a sense. Like, we can have a computer program on your laptop that says, give me any program and I'll compile it down into these Boolean circuits with some memory for you. And that's a valid approach. But it then draws you back into each time you get a compiled program that the electronic computer tells you to build in the lab, well, then you have to debug that program. And even though it works on the computer, it's very likely that it won't work very well in the lab, and you'll have to spend months or years debugging it. Also, its size will probably change. If you have a bigger program, you'll need a bigger set of molecules to execute it. So on one side, you might say we want a bigger instruction set to make it more powerful. I don't think we can do that with existing chemical hardware. And on the other side, you might say, I want no instruction set and just do large circuits. And I think that then defeats the purpose of making it so you don't have to debug the circuit every time.
What kind of iteration timescale are you thinking could be achieved with this? So obviously you mentioned that building DSD circuit from 0 end could take months to optimize. What do you envision being the time set? Like, could I just order some more DNA and have it arrive the next day and use that for the memory, or is it even quicker than that? Do I do something to the mixture itself?
Yeah, I think it should be quicker than that, ideally. I don't know if I'll get it to work. We'll see. Maybe someone else will figure out the right way to get it to work. But ideally, if I could wave my magic wand and have some stored program computer, who cares which architecture, work, you should have the processor or parallel processor set, and I should only have to make that one time. I anneal like, I don't know, tens of liters of this stuff, and I don't have to make it again for 10 years, or a year, maybe. Now, you can just take that and add the memory to it, but you do have to encode the memory somehow, and that's probably going to be on a different set of tiles. But you should be able to have one tile, and you just specify the address on its sides and the initial information on its surface. And that should probably be possible to do with a very limited set of strands. So you shouldn't need to order new strands each time. Just anneal one origami or your sets of input origami with the appropriate addresses and surface information. And then mix that with your universal mix. It's kind of like punching holes in punched cards. You spend some time getting those punch cards ready, but then you don't have to go rewire the computer. You just feed the punch cards into the device, and it can execute at that level. So I would like to be able to, I mean, this is optimistic, but I would like someday to be able to run any arbitrary program within 24 hours of having conceived it.
And can you imagine getting even better than a punch card approach? Can you imagine then actuating this annealing in an automated way, maybe integrating electronically, something like that?
Absolutely. So one of the things, Caltech is a fun place to work, but one of the many exciting things is they have the Echo acoustic liquid handling robot. And if any of you have used that, it's awesome. So it works by having a little speaker underneath your tray, and it plays a sound, and that flicks a droplet from one tray to another in a very controlled manner, and you can have 25 nanoliter resolution on these transfers. So something that would have taken me like, I don't know, 4 hours to pipette in the past now is like 10 minutes. And it kind of makes my thumb hurt just to think of how much time I've spent doing that. But you're certainly right. We can have these sorts of very fast electronics and liquid handling robots prepare these devices for us. You could also do something where you have your punched card, in quotation marks, DNA origami, or however you're encoding the information, pre-made, pre-annealed, but with no information encoded on them, and then flash it with some series of blue or UV lights that pattern the surface in some way. I don't know how to do that, but you could imagine lots of more exciting ways to do this. The other limitation, though, is that I'm imagining these devices will be quite slow, with cycle times on the order of quite a number of hours, presumably. So even if at some point the limiting factor then returns to the execution of the program as well.
So that I was actually going to ask about that. I don't know if this is quite a naive question, but so do you pay a performance penalty by being able to do general computation in the same way that like application specific integrated circuits are very, very fast at doing one thing? Are they analogous to the current way that we build DNA circuits versus kind of a CPU which is able to do anything but is generally a lot slower?
Yeah, probably in some ways. If you know the optimum ASIC application specific integrated circuit, if you have an optimum design, then it probably works faster than your stored program computer. But the stored program computer can, that's if everything's working beautifully, perfectly, like in the electronic circuits where, you can have twice the number of transistors and you don't have to worry about, leak where one transistor feeds information to another transistor halfway across the circuit. So right now, I think the biggest issue that I've come across on the experimental side of strand displacement circuits is leak. And that's where you spend almost all of your time trying to fix leak. And so the ASIC circuit might be faster, but it might use more individual components, because the stored program computer can reuse its components. It can have its memory, pull in some information, run one cycle of computation with the processor, but then it reuses the processor each time. So depending on the specific algorithm, the processor size might be smaller, and therefore the potential for leak, which scales exponentially with size of the processing circuit, is going to be much smaller. So you can mitigate the leak again with like the leakless architecture, but it still is really, really hard to do. So I would say that many of the types of things that I want to build, molecular algorithms I want to execute, are already would have too much leak in order to run with anything that's not reusing its components. Because if you have 10 times as many components, you have 100 times as much leak, and it just isn't going to work.
Is the cycle time on the order of hours because you're synchronizing maybe the whole solution of these computational components? Have you looked into maybe asynchronous parallelism? Is that something that's possible?
Yeah, so I think this will be asynchronous. So it's not every single step will be 10 hours or 5 hours or whatever. But on average, I would expect the steps to take that long, because the fastest reactions are going to be on the order of minutes, and you're going to need many of these reactions. Quite possibly you won't just be using 7 nucleotide toeholds. You'll need some slower things as well, and so all of that is going to make your steps on average be on the order of 5 to 10 hours, presumably. But yes, asynchronous is key. I still think it would be interesting to demonstrate a stored program computer without asynchronous computing, with a oscillator like we talked about before, a central oscillator. I still think that would be a useful demonstration, but it's much, much less powerful. And so ideally we just skip to asynchronous computation.
And can you do kind of multiple distinct computations that have no relevance to one another in the same medium?
So Boya was asking earlier, how do you have your processing tiles read information from different inputs? And for that, the processing tile needs to know I'm going to look for memory tile A, and then once I find that, I'm going to transfer its information to memory tile B. That's one transfer instruction, and then you'll search for your next one at transfer C. So if some of your processing tiles are, their surface reaction says I'm looking for address A, and another subpopulation says I'm looking for address D, well then they're already going to be partitioned into running the code at address A and address D in that sense. So it's kind of built into the system there.
Sounds like it is going to be a lot of orthogonal sequence design problem. Will there be?
So it depends on a few things. The surface reactions shouldn't require that much because you only need a limited set of surface reactions because you're reusing the same components in different geometric locations. That's the reason to use the surface reactions. The place where you need orthogonality is going to be on the addresses of the tiles because you can only have as much memory as you have address space. That's an open question, but Lulu's tile displacement paper, I think, has 11 bits of information on the side that are encoded in the sticky ends on the side. So conceivably, you could get quite a bit of address space there. But yeah, that will definitely be an issue. One way to mitigate that is to use one universal address, have all of the tiles be able to bind with everybody else, but only have them query the address encoded on the surface of the tile when they bind. So you bind to a universal neighbor, you check its first 4 bits of information or first 10 bits of information that encode its address, and you say if those 10 bits of information match the address I'm looking for, well then I'll do the transfer instruction. But I'm going to first check that address tag on the data encoded at that memory tile. That would be one way to get additional memory space, but it might make things slow because then you have to search through a lot more universal address space. Another thing to keep in mind is, at least right now, I'm targeting 10 to 100 lines of a program. So maybe you don't need that much address space to execute relatively simple programs. And that might seem really small, but for reference, I think the biggest molecular program that I've seen so far is about 130 strands, and that can be encoded in one line of a MATLAB program. So if I open MATLAB, I could write that entire square root circuit in one line of code. Even though it's quite elegant for the molecules to do it, it still is just really one step of a stored program computer equivalent program. So 10 lines we could do 10 times more than that potentially. And I don't think you would need that much address space to encode 10 tiles worth of memory instructions. But to get to 1,000 or much bigger, then yeah, the orthogonality will be in the address space of your various tiles.
So are these memory tiles kind of, are they diffusive? So are there any way, have you thought about any architectures where you kind of have maybe a memory array on a surface where you kind of actively go and fetch something at position X and Y, which might then enable you to massively increase the storage capacity?
Can increase the storage capacity? Yeah, I like that. Your hardware will probably be more complicated, and again, that might be beyond the limitations of, like, what if I squint my eyes and cross my fingers and hope we can implement it in the lab. I think already that might be beyond what we can currently do, but maybe in 5 years we would be able to build something like that. The other thing you get to with, if you took all of this, say, and just put it on one array, Like, don't have anything diffusing around. Just have one array immobilized on a surface and have it be 10,000 tiles by 10,000 tiles. The one issue you run into then is for information to propagate from one far edge of the 10,000 by 10,000 array to the other edge can take quite a bit of time, and you might need quite a bit of wire crossovers, equivalent to a wire crossover, at least in an electronic circuit, where that takes up quite a bit of space to get two orthogonal wires to not transmit information to each other if they're not supposed to be connected. So you get into those sorts of scaling issues if you just try to make everything on one big array. You also get to yield issues. So making that array will be quite challenging, but also probably the bigger the array you get, the lower the yield is going to be. So dimerization, you can get quite good yield. The Mona Lisa has, I think 8 by 8. I could be forgetting that exact number, and that still is reasonable yield, but it's not certainly well below 100. And if you went up to 10,000 by 10,000, I think your yield would suffer quite a bit.
So where are you on the experimental front? Is this completely theoretical? Have you started any experiments?
Yeah. Yes to the appreciating the question, not yes to have started experiments. So what I've talked about so far is theory and simulation. In the lab, I think that two of the most challenging components are getting synchronization, as we've talked about, so that all of your circuits components know when to execute. And then also getting the addresses to bind, transmit some sort of information that they have bound to propagate the next transfer instruction, and then unbind. So bind, do something, and unbind. Those are two things that I'm exploring in the lab. The binding and unbinding is a small step forward from the existing tile displacement paper, which I did not work on, but I'm trying to extend that to be able to do these sorts of operations. And then the synchronization, I have done a fair amount with, but it really boils down to an oscillator. So anything that can execute instruction 1 and then instruction 2 and then instruction 3 and instruction 4, where these instructions might loop, is an oscillator, right? Because it can loop through on itself. So we need to get a good motif for building these types of oscillations. In the architecture that we've been talking about with all these tiles, each population of tiles will need to essentially be its own oscillator, in that it executes its instruction and then it waits until everybody's caught up and then it executes its next one. That's like a bunch of spikes that turns into an oscillatory signal if you want. And you'll need a bunch of different ones. And right now, building those types of oscillators is really hard. And it's been done with enzyme-free circuits with up to about 3 oscillation cycles, but they peter out, they damp quite quickly. And it's been done with enzymes with a substantially more number, maybe 10 to 30 oscillations. But then enzymes also will go and try to transcribe your origami tiles and cause all kinds of other issues. So I'm trying to avoid using them if possible because of their interactions with nanostructures. So then if you go back to DNA oscillators, the issue comes to fuel consumption, energy consumption. How do you pack in more energy into your system to drive the oscillations longer, but then don't cause terrible leaks to happen that just destroy everything? And then also you're going to be loading this, presumably you have an oscillating signal, but you're going to have it driving some downstream process. So you're taking energy out of the system, so you need to also compensate for that. So that gets into my main body of experimental work, which is trying to build a power supply, a battery that can drive dynamic DNA circuits for much longer than they've been driven in the past. I'm trying to get to 10 cycles for the initial round. I'd be quite happy if that works with these battery devices, and then ideally I'd like to scale. I think it's possible to get it up to 100 cycles. Hard, very hard, but possible to do. So that's where my experimental work has been, is developing these sorts of primitive motifs. What that chemical battery is a high concentration reversible reaction. It's analogous to a pH buffer where you have an acid dissociating into your hydronium ion reversibly. And we can build these types of high concentration reversible reactions as buffers with DNA, which is something I showed in the past, but I only did it with a single strand of DNA. So now if you want to buffer a circuit or a structure, then you need much more elaborate motifs for actually buffering those types of devices. And that's where I've been experimentally, is trying to buffer complex enough motifs to drive an oscillatory signal for 10 plus cycles.
That's really cool. Is this battery kind of, it's a buffer, and then once you've used up all of that buffer capacity, that's it? Or is there any way to replenish it dynamically whilst it's happening?
Yeah, great question. It's fun talking with y'all. It feels like a miniature, like a breakout session at a DNA conference. It's very exhilarating after all of COVID isolation. But you can recharge them. There's a few different ways people have done it. You could just pipette in more of the circuit at some point, but then you also have waste accumulation. So one thing that a master's student and I worked on at Johns Hopkins, Chinyu, is a pumping system that continuously resupplies your it can take any circuit and makes it run in a pump system for multiple cycles. And this is actually taking a step back. I like to think of it as like plugging your device into the wall, into a socket in the wall. You can run forever. If you aren't plugged into the wall, you have the buffer battery. Well, then it can run for a certain number of cycles before the battery dies. And then maybe you plug it into the wall to recharge the battery. But if we're just for now conceptually looking at the plugging it into the wall motif, you don't need the battery at all during that. So for this, you can take any existing DNA circuit, and we did it with the 2006 C-Lig original enzyme-free DNA strand displacement gates. And we just took his device and we put it into the pump setup, very simple chemostat pump setup, and showed that we can get it to run, I think we did 10 cycles of different inputs that were being flowed into the system, and the circuit responds appropriately, adjusting its output according to the inputs. So that's how you can recharge any circuit. As long as it's connected to the pumps, you can keep getting it to work. You don't need to make any chemical modification, which is kind of a neat thing, because there's a lot of circuits out there that maybe, well, if you could keep them working for more than one cycle without any chemical modification, it'd be quite interesting. You can do that for the buffer as well. The math for both the chemostat and a set of buffering reactions actually works out to be the same. The ODEs are identical, or nearly identical. So they're doing the same thing of regenerating your reactions over time. But one of them is consuming a depletable resource in order to do that, and the other one is using a mechanical motif to do that. But you could use the plug into the wall pump motif to regenerate any circuit, including a buffer circuit, and then unplug it from the wall after the buffer is recharged, let it run for 10 cycles, disconnected, and then plug it back in when you want to recharge it.
Oh, nice. Okay, and in the time we have left, I thought it might be nice to get your perspective on some more personal questions, particularly with the transition from grad school to postdoc still fresh in your mind. Were there any big surprises for you in that transition that you weren't expecting?
Yeah, lots of big surprises. I don't know that I have time to enumerate all of the surprises. But I think that probably the biggest surprise is just knowing that in a PhD you have all the time in the world, and you're trying to work towards your papers, and maybe if you're your fourth year or fifth year, you're working towards your dissertation, if that's how your program works. But early on, you're just exploring. I think in the postdoc stage, it feels much more like you're exploring, but you're building the groundwork for what you want your next stage to be. So this is your chance to, with no tenure clock, to get the hardest pieces of your long-term goals working, so that when you do have your tenure clock, if you're so lucky, then you don't have to build those hardest initial pieces. You have them under your belt all ready to use. That to me has been one of the biggest differences between PhD and postdoc.
And did you always know you wanted to stay in academia? Have you had any temptations to sell out and go to industry? Or
well, this might be controversial, and I hope it doesn't has too many repercussions, but I actually don't like academia. I think that there's a lot of things about it that are quite negative, academia as a whole. But I love molecular programming, just like all of you do, and presumably all of your listeners. It is so cool to be programming with molecules, and it really feels like we're part of a second computer revolution that is going to really change how science and technology works. Maybe 10 years from now, maybe 100 years from now. We don't know the time frame, but this is a paradigm shift in how humans are interacting with matter. And being part of that is so exhilarating. So I want to keep being a part of that. I don't see clear paths to do the type of things that I want to do for molecular programming without being in academia. Therefore, my love and joy of molecular programming supersedes my distaste for the world of academia. If I were so lucky to be able to continue on this path, or fortunate perhaps is a better word than luck, then I would like to use academia as a launching point for molecular programming in industry. Quite likely many other people feel this way, whereas if we get the foundational science far enough along, well, then we can spin off startups and we can start the Intels and whatnot of molecular programming. Presumably not just one person. It's going to be a bigger cluster. All of us who managed to stick along. So that would be the dream. Along those lines, though, I would like to unveil another small project, or not small project, big project, that myself and a few other students at Caltech have been working on, and we'd like to invite participation from other people in the field. We've noticed that there's this trend where it's getting harder and harder for young incoming students to wrap their mind around the field, see what it is, and start making their contributions. So like if you're a brand fresh student, one, you have to identify molecular programming as a field, which most college students don't necessarily have that information. And then two, you have to go find this like 10,000 pieces of lore that are scattered across all these different papers that might be behind paywalls, and you don't even know what papers they are. If you're lucky to have a great advisor, like I've been, then you can be told which papers to go read, but they all, modify each other and supersede in different ways. There's not one central location for that. So Namita Saraf and William Poole and I have been trying to find ways to create a textbook for molecular programming. And we'd like to do this as a collaborative process. We think that there's this groundswell of energy and support from early career molecular programmers, from you here and from our listeners, where we want to build and grow this field and reach this exponential stage where we're not bringing in one new researcher a year, but many. And I think that's what molpigs is kind of getting at. We're building this community where we can work together. So for the textbook, we'd like to invite interested people to to join us on the editorial board to decide what the textbook is about, although we have some initial concepts and we'd like it to be about the field as a whole. And then we'd like to invite experts and passionate molecular programmers to contribute their section or chapter or paragraph on what they're most knowledgeable about to the textbook to be edited together, so that we can get one central location, all of the mature principles of molecular programming to draw in and inspire and support early career molecular programmers as we proceed to the next stage. There will be more information about that, but molpigs seems like a great place to be bringing this about, and I'm hoping that many molpigs subscribers will be interested in hearing more and maybe contributing to this type of grassroots project.
Yeah, thanks for the announcement. I know I'm really excited by that idea, and yeah, I'm sure everyone will be. Is this going to be kind of like a traditional textbook? Are there going to be any maybe an open source collaboration, or what kind of approach are you taking?
Yeah, we'd like it to be open source. So our motivation here is not money. We're not going to get rich. We want to drive the field. It's also not altruism either, though. Like, we don't just want to have this as a line on our broader impact section of an NSF. We want this to drive and stimulate the field. So to do that, we think keeping it open source is the best option. It might be for the first 1,000 copies or so, it might be $5 or some nominal fee so that we can recoup our publishing costs. But if we're able to find those publishing costs in other ways, which is what we're looking for right now, then it would just be fully open source and free. One other thing we're working with is figuring out how do we update it over time. So right now we want it to be, here's what's known, not the cutting edge, but here's what's known that's not really going to change that much about molecular programming, so that early career people can wrap their mind around it very easily. But over time, that cutting edge or bleeding edge is going to be changing, and so we can incorporate and change and add more content. So we'd like to find ways to not just make one round of the textbook, but make it updatable. Probably means an electronic copy, open source, obviously, like we said. But we also really want to have like a tangible thing. So the open source copy presumably will be free, but I think you'll be able to like pay the printing costs and get a physical thing that contains all of this wisdom and lore concentrated in one place, and you can flip to whichever page you want at your leisure. So presumably it'll have both of those aspects.
I'm very excited about this now. For what background will this book be targeted? Like pure, will it be mainly for engineers? Will it be quite a mathematical textbook, or will it be kind of more high level for anyone just finishing up their undergraduate degrees, hoping to move into graduate school?
Yeah. We'd like it to be for any undergraduates, senior undergraduates, and early graduate students too, as they're ready to learn about molecular programming or have just started learning and really want to dive in and get all of the nitty-gritty details, like, I don't know, how do you get kinetic rates for four-way strand displacement? Like, have all of that in there. It's really targeted towards that. It could also be used for incredibly motivated high school students. I probably wasn't motivated enough in high school to do that, but we've seen a lot of high school students who have participated in various labs that I've been in who are as advanced as a college student. So I don't want to restrict it just to that age group necessarily. And then also interested professors who might want to use it to teach, or teachers could also use it in that manner as well for classes. But to try to answer your question in a little more detail, we want to have it have all of the necessary theory and mathematics to understand how these pieces work, but not so dense as to scare off a scientifically literate, mathematically literate college student who maybe doesn't understand all of the intense intricacies of computer science. So yes, math, but not only math, and you don't need to be a abstract mathematician to understand it. For authors and editors who this pitch is targeted towards right now, who might want to contribute, we want everybody, if you think you're a molecular programmer, and you have time, so presumably earlier stage the better. You don't have to be a professor with 20 people in your lab in order to be considered an expert to contribute to this book. But if you're working in molecular programming and you're excited by it and you have time, then we want you if you're a theorist, we want you if you're an experimentalist, we want to be able to reflect all aspects of the field.
And for these people who are starting their journey in high school or in college, what kind of advice might you tell them? Might you put in the preface to kind of help them on their way?
Of the textbook, I can't say right now because we haven't written that, and this is certainly not my project alone. Right now, it's conceived by Namita and Will and myself, but hopefully very shortly that leadership will expand to broader groups. So I don't know what the introduction will say, because that will be however many people are participating in it. We'll get to decide what the introduction says. But if I was just speculating a little bit on high school students getting into molecular programming independent from the textbook, I have two thoughts. One is that the Steve Jobs and Bill Gates and Elon Musk and all of the people in traditional, what we consider traditional technology, like molecular programming aside, who are not the first generation, those people for molecular programming are sitting in high school classrooms right now. So like we are the Turing and von Neumann generation, or perhaps that's like Ned and Winfrey, perhaps, where people who might not be as big of names, myself at least, but that we are that first generation. But the people who are going to take what we're doing and transform it into this second computer revolution, this chemical computer revolution, they're still in high school, maybe in elementary school. And so if we want to draw them into this profound paradigm shift, we need to reach out to them and try to break down these barriers and draw them in. So more plans we can make now are going to help the field in 10 years if we can start to draw these people in. Advice that I would actually give to them, I think what's helped me most for molecular programming is trying to say, what do you want the world to look like in 100 years or 50 years? Some long-term thing, some lifespan type of timescale, and then say, well, how do we work towards that? Because I think if you get into science, if you look at what we do day to day, it's like we pipette a drop of liquid into another drop of liquid. That's quite boring to everybody, I think I can safely say. But the longer term vision of why it's interesting to pipette that clear drop of liquid into another drop is because of this paradigm shift that you have to really look on the long term to see. And I think high school students are uniquely positioned to, the groundwork has been done for molecular programming to take off. And so they're positioned to capitalize on that in some really exciting ways.
What a great way to end this podcast. Thank you so much for joining us, Dominic. I really had a great time talking with you. I'm sure everyone else will say the same. It's really interesting stuff. Dominic will be staying around on our forum for an Oink Me Anything, as we call it, in which you can ask him any questions you have, which I'm sure will be many, about his work, life, or this textbook, or anything really. So please do join us over there. If you haven't yet joined the forum, you'll find an invite link in our newsletters, or you can sign up directly at talk.molpi.gs, molpi.gs. This is it from us for 2020. We hope you have a safe and happy holiday wherever you may be, and that will start the new year with renewed hope. And thank you for listening.